Hey guys, it's Jessie. I'm going to be going over the Conjugated Systems Recitation packet. I know at the top it says week 3 and we are more than 3 weeks into the semester, so I'm guessing that's a typo. But anyways, let's jump in with question 1. Okay, question 1 asks us to rank the following dienophiles from least to most reactive in a Diels-Alder reaction. So the thing that we're interested in for each of these compounds is the double bond, and then specifically what the substituents are that's coming off of the double bonds. So for this first compound, we have this ester type group coming off of this side of the double bond, and then this ester, or I guess we could just circle the carbonyl carbon of it, coming off of the right side. So we want to determine if those two substituents are adding electron density into the double bond or if they are pulling electron density away from the double bond, and typically that's done through either resonance or induction. So I'm going to look for resonance structures. The first thing that I like to do is, if there's a carbonyl carbon, we can always just pop those electrons up onto the oxygen, creating a negative charge on the oxygen and a positive charge on the carbonyl carbon. And that could be done on both sides. So again, we could have have those electrons move up, creating a negative on the oxygen, positive on the carbonyl carbon. And then from there, we could draw another resonance structure with the double bond here, moving either to the left or to the right, depending on which side we've shown our positive charge. So let's say that we popped these up, making a negative here, positive here, and then we could pop those electrons up, creating a bond here, which would then, we'd still have a negative here, but our positive charge would be down on the bottom right corner. And then the same thing could happen over here. If this was negative, this was positive, we could have the electrons come over here, creating a positive over here. So overall, there's going to be a partial positive on both sides of this double bond, meaning that it is electron deficient. So both of the substituents coming off of the double bond are considered electron withdrawing groups. So I'll go ahead and highlight both of them. These are both electron withdrawing groups. So moving on to the second one. Again, we have this double bond here with substituents coming off both sides. We've got a methyl group here and here. There's no way to make this resonate because there's only the singular double bond. So those two substituents aren't going to have any resonance effects. However, they can have just a little bit of induction, which is going to push a little bit of electron density into the double bond. So it's not super strong. It's a relatively weak donating group, but they are still considered donating. So I'll go ahead and highlight these in a different color. These are electron donating groups. And then for the last one, we have this double bond here with a methyl group off to the left and a carbonyl carbon or ketone off to the right. So as I just mentioned, the methyl groups are weakly donating. So I'm going to highlight that in blue again. Blue is electron donating groups. And then as we saw with the first compound, this carbonyl carbon has the capability of resonating its electrons up onto the oxygen, creating a negative charge here and a positive charge on the carbonyl carbon. And if there's a positive there, we can then have these electrons come over here to fill in that positive, which would create a positive charge over here. So overall, we're going to have a partial positive on one side of our double bond. And this group, oops, sorry, wrong color. This group is an electron withdrawing group. So now, whether or not the donating and withdrawing groups are activating or deactivating, we have to think about the mechanism for a second. The dienophile is going to be attacked by the diene, which means that the thing that is more electropositive, or in other words has less electron density in the double bond, is going to be more reactive. So the thing with the most reactivity is the thing that has, the two withdrawing groups. This is going to be most reactive. So in this case, it would be 3 because we're going from least to most. The second most reactive would be the one that has one withdrawing group and one donating group. So over here, that would be 2. And then the least reactive is the compound that only contains donating groups, because donating groups are deactivating. If it helps you to remember the donating is deactivating, I think that's kind of helpful. All right, moving on to question 2. We're now asked to draw curved arrows or using curved arrows, draw the mechanism for the following Diels-Alder reactions, and then predict the products. So I think it's helpful to just remind ourselves what the most basic Diels-Alder mechanism looks like. So I'm going to draw that up in this corner. So we have the simplest diene that we can make, and then the simplest dienophile we can make. And when those two come together to react, the mechanism looks like this, where we have first one of your dienophile or diene double bonds comes out and attacks, which prompts this double bond to move over here and this one to move here. And then our product is a cyclohexene ring. So we're basically just going to be doing this over and over again. We just need to make sure that we can get our dienophiles to be in the S-cis conformation, and then we need to pay attention to any substituents that might be coming off of any of these positions. So let's take a look at question 1. As we can see, this is not in the S-cis conformation, so we're going to need to rotate about this single bond in order to get it into the correct conformation. And then the dienophile is oriented kind of upwards, but we know that there's going to be 2 bonds that eventually form on either side of that double bond. So I'm going to quickly, again, rotate this bond so that it can be in the proper conformation in order to do the reaction. So it should look something like this. And then we're going to want to create new bonds. I'm going to change colors here. Eventually we're going to have a bond coming from this double bond over here to here, and from this double bond here to here. So to draw out the actual mechanism arrows for that, I'll show this one coming out and attacking. Oh, let's change back into our regular pen. So this double bond attacks the dienophile, which then prompts this to come over here, creating the new bond to close off our cyclohexene ring, and then this one pops down here. And when we do that, the product is going to be, again, a cyclohexene ring with all of our former substituents. So from the diene, we had these 2 methyl groups that were both present before. So we're going to draw those in. And then on the dienophile, we had these 2 ketone groups coming off of the double bond. And you'll notice that this double bond was trans to begin with, so we had 1 group on top and 1 group on bottom, which means that in our final product, we should have 1 substituent facing up and 1 substituent facing down. So we'll draw 1 on a wedge and 1 on a dash, and these are both ketones. So that's what our final product should look like. And just as a reminder, the bonds that we created were this bond here, and this double bond. So we broke 3 bonds initially, we broke these 3 bonds, and then we formed those 3 bonds. Moving on to the next question, we have our diene and our dienophile. And the diene is already in the S-cis conformation, so we don't need to worry about rotating that. And then, again, we're just going to create bonds from where this double bond was to where this double bond is, and then where this one was to where this one is. And that will be our new cyclohexene ring, and then again, one of these double bonds here will just move down to the side. So let's draw the arrows for that. So this arrow comes out and attacks the dienophile, which prompts this arrow to move here and these electrons to move here. And when we do that, our product should resemble a cyclohexene ring with all of our remaining substituents. So in this case, the diene had this ring structure here, which would be coming off of, those carbons right there. So I'm going to kind of pencil them in on a wedge for now, and then we can redraw it in a second if we need to. And then off of the dienophyl, we had these two COOH groups, and again, they are trans, so one is on above and one is below the double bond, which means that on our final structure, one should be on a wedge and one should be on a dash. So let's draw those in as well. So this is technically correct, but we could also redraw the structure with a little bit of a different format to make that bicyclic structure a little bit easier to look at. So I'm really bad at drawing these structures, so give me just a little bit of grace. But if I were to imagine that I'm taking this molecule and rotating it so that I can see all three of the different bicyclic portions of it, I would draw something like this. So kind of hard to look at, but that is the bicyclic structure. We have this double bond here, and then we could just point this one up and this one down. And that would also be correct. This next mechanism shows the diene in S-trans conformation, so we're going to need to rotate this single bond so that the diene is in the proper orientation in order to do the reaction mechanism. So I'm going to redraw the diene. So I've just rotated it. And then the dienophyl in this case is the triple bond right here. So the mechanism still is going to look exactly the same. It just means that when we have our finished product, instead of just having one double bond in the cyclohexane ring, this will also be a double bond. So to draw the mechanism arrows, it's the same thing as before. We're going to have the diene come out and attack the dienophyl. Then the electrons here will come and form a bond on the other side and pop these bonds, or pop those electrons down. And then the product will again have that same cyclohexene ring as a base structure. And then, because this had a methyl group to begin with, there will still be a methyl group over here. And then on the side of the dienophyl, we have these two cyano groups. And again, we lost one of our double bonds, but the other one will still be present. So we will have a CN group here and a CN group here and a double bond here. And because of that double bond, both of these carbons are now sp2 hybridized, so everything is planar, so we don't need to worry about drawing wedges or dashes here because everything is flat and planar. So question 3 asks us to draw the diene and dienophyl pair that could be used to synthesize the following compounds in a Diels-Alder reaction. So basically we're just working backwards to figure out what our starting materials were that could have created these products. So remember from question 2 with this basic reaction mechanism, we're starting with something that has two double bonds and then a single double bond and forming the cyclohexane ring. And now we just need to work backwards. So I'm going to identify where my cyclohexane ring is, and then from there, think about which bonds need to be broken. So if we formed this double bond here, that means that the original diene should have had double bonds here and here. And the dienophyl should have had a double bond here, which means that these two bonds need to be broken. So I'm going to pencil those in. So we know that these bonds need to be broken because those are the ones that are formed in the reaction mechanism. And our initial starting material should have double bonds here, here, and here. So to draw those out, I'm going to do kind of a retrosynthesis arrow because we're showing that this product was made from the following reactants. And now we basically just need to redraw what is on each side of the broken bonds. So the dienophile would have looked something like this. And again, that's from here. And then, did I call that the dienophile? That was the diene. I don't know if I said that wrong, but it's fine either way. So that's the diene. And then the dienophile is what's on the other side of the broken bonds. So those are the two reactants that would have been used to make the product shown here. And again, just thinking about it in the forward direction, if we were trying to have this reaction take place, the arrows would look like this. And that would get us back to our starting material. For part B, again, we need to identify where the cyclohexene ring is and think about what bonds were formed and what bonds were broken in order to make it. So I can see that there's a 6-membered ring here with that double bond off to the left. So that is our cyclohexene ring. And then because the double bond is here, we know that the original diene would have had a double bond on either side of where the current double bond resides. So again, that's here and here. And then the dienophile would have been, basically if we were to break those two bonds, the double bond should be between these two carbons here. So again, I'm going to pencil that in. So because we know where this double bond is right now, we know that the initial diene would have had a bond here and here, and the dienophile would have had a bond here. And we're going to break those two sigma bonds. So now to redraw the starting structures, if we broke these two bonds, that means that the diene now consists of this cyclopentene ring. So this ring is still intact. It's just the cyclohexene that was broken. So I'm going to draw this cyclopentadiene ring. So that was our original diene, and our dienophile is this structure here. And because these are both facing down, because these are both facing down, we know that the two substituents would have been in a cis position relative to one another. So I'm going to draw this double bond with two cis substituents, and then it's CO2CH3 for both of them. So this is our starting material, and again, just to prove it to ourselves and think about what this reaction mechanism would look like. If I were to redraw these arrows, this would come out and attack here, and then there, and then there. And if we had that mechanism take place, the final product would look like the starting material that we started with. So that's part B. Moving on to this last one. This one's a little bit tricky because I'm seeing two cyclohexene rings here. So we've got this one off to the left, but we also have this cyclohexene ring on the right. And I think technically, in theory, you could do it both ways. I'll show you what it looks like, and I'll show you why it's probably not super practical to have it done one way versus the other. And what I mean by that is, if we were to assume that this is the ring that was formed in the Diels-Alder reaction, we would have to imagine that if this was the double bond in our cyclohexene ring, the original diene would have had a bond here and here. And then that means that these are the bonds that were formed in the reaction, and this was the original dienophile. So just to draw those all out, if we're imagining that this is our diene, this is our dienophile, and these are the bonds that were formed in the reaction, that means our starting material would look something like this. And now you're probably looking at this and thinking, okay, that's weird. Because if we have a carbon here and a carbon here, both of these already have 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds, which means that they wouldn't have this bent configuration. They would actually be linear, because this is now sp2 sp hybridized, because there's only 2 electron domains. And same here, there's only 2 electron domains, so they should be sp hybridized, which means that they would be linear. So if I were to redraw them in a linear fashion, well, I guess we're just going to redraw all of it. It would look something like this. Which I think in theory that molecule could exist, but it's not incredibly stable. We know that these cumulated double bonds are not seen very often in organic chemistry. So that's a pretty good indicator that this isn't the route that we want to go. And then on top of that, if we were to compare the reactivity of these two starting materials versus the reactivity that we could make if this was the cyclohexene, you'll see that these are not as reactive as what I'll show you in a second, the proper way to do this one. So anyways, this is technically possible, but probably not likely to happen. So I wouldn't recommend going this route. Okay, so what is the proper way to do it if not that? So again, we have this other cyclohexene ring off to the left, and if the product has a double bond here, that means that the initial starting material would have had double bonds on either side. These bonds would have been broken, and there would be a double bond here for our dienophile. So let's draw that out. So the diene would have 2 double bonds here. These are the bonds that were formed in the reaction mechanism, and the dienophile would have a double bond here. This means that our starting material should look something like this. So these are our 2 reactants, and as I mentioned earlier with reactivity, we now have this carbonyl carbon directly adjacent to this double bond, meaning that if we were to show resonance structures, we could have a positive here and a negative here, or we could have those electrons move here, these electrons move here, which would put a positive here and a negative here. So there's 2 partial positives, one on either side of this double bond, making this electrophilic, meaning that this is a relatively reactive dienophile. So this is the product that I would expect, or these are the reactants that I would expect were used to make this product. All right, moving on to nomenclature. Question 4 says to draw the structure of the following compounds. So this first one is M-dibromobenzene. So I'm going to start with the parent structure, which is benzene. And so the M indicates that the substituents are meta to each other, and dibromo indicates that we've got 2 bromines. So I'm going to draw the first bromine, and then from here we need to figure out ortho, meta, para, because it's M, so we know this is the ortho position, that's the meta position, and that's the para position. So meta indicates that the other bromine will be right there. All right, part B says p-nitrotoluene. So let's draw the parent structure, which in this case is toluene. Which looks like this. And then we have a nitro group in the para position. So again, this is ortho, this is meta, this is para. So we're going to draw nitro in the para position. Part C is 2,6-dimethylphenol, or phenol, however you want to pronounce it. So let's draw that parent structure. So there's phenol. And then we can't use the ortho-meta-para designations because in this case we have 3 different substituents. We have the OH from the phenol, and then we have the 2 methyl groups, one on position 2 and one on position 6. So I'm going to draw in our numbers. Phenol is going to have position 1 because it's the parent. And then we need a methyl group on 2 and 6. So methyl here and methyl here. And then the last structure that we need to draw is 3,3-dichlorocyclopentene. So this is not a benzene ring. I think this is just review from CHEM 1, just to make sure that we're not confusing our previous naming of non-aromatic compounds. So let's draw cyclopentene. And then it's 3,3-dichloro. So in this case, the highest priority group on this compound is the double bond. So if I were to number these, I would number through the double bond. So 1, 2, 3, 4, 5. And I could have now numbered counterclockwise if you want, as long as, again, you're numbering through the double bond. So in this case, this would be 1, 2, 3, 4, 5. And then it's 3,3-dichloro. So I would just draw 2 substituents coming off of carbon 3. And that is the structure. Okay, so question 5 asks us to identify the pi orbitals and the number of pi electrons in each of the following compounds. So the long way to figure out a pi orbital would be to look at each individual atom in this molecule and draw out its molecular orbital diagram or its atomic orbital diagram. Think about how many bonds it has, how many unpaired electrons you need, go through the whole promotion hybridization, and figure out if there is a p orbital remaining. And I can work through one example of that just so you can see what I'm talking about. But then from there, I'll show you just the shortcut for figuring out where the pi orbitals are. So let's just pick this carbon. You'll find that basically all of these are going to be the exact same. But if I were to draw the molecular orbital or the atomic orbital for this carbon, I would start by showing increasing energy as you move up. There's going to be your 1s orbital, 2s orbital, and then you have 3 2p orbitals. So 1s, 2s, 2p. And then looking at a periodic table, we know that carbon should have 6 total electrons. So I'm going to go filling from the bottom to the top. 1, 2, 3, 4, 5, 6. Now we know that we need to have half-filled orbitals in order to make bonds. So looking at this carbon here again, we know that it should have 4 bonds because its formal charge is 0. So we have 1, 2, 3, and then an invisible hydrogen making our 4th bond. So we need to have 4 unpaired electrons in order to, 4 half-filled orbitals in order to make 4 bonds. So to do that, we need to promote one of the electrons. So I'm going to show this electron being promoted up into the p orbital. So now we have So now we have 4 unpaired electrons, or 4 half-filled orbitals. And then to figure out how many of them are going into hybridization, we need to think about the number of electron domains in this carbon. So again, we have 1, 2, and then the invisible hydrogen is 3. We have 3 electron domains, which means that 3 of these half-filled orbitals are going to become hybridized. So I'm going to shrink this all down a little bit to make room for hybridization. And in order to hybridize, we need at least 1 s orbital, and the remaining will be p orbitals. And again, we said that there's 3 electron domains, so we need to have 3 of these orbitals being hybridized. So now our diagram should look like this. Oops. So we still have our 1s orbital, which remains untouched. We now have 3 sp2 orbitals, and then we have our remaining unhybridized 2p orbital. Which means, all this to say, that this carbon does in fact have a p orbital. And if there are 2 p orbitals directly next to each other on adjacent atoms, then they can overlap to form a pi orbital, which is what's going on with all of the double bonds that you see in this structure. And the shortcut is to just recognize that anytime there's a double bond on an atom, it's going to have a pi orbital in compounds. So all I'm doing here is looking for places where double bonds can be formed. So obviously we've got these 4 that are already shown, but because we have this lone pair here that's adjacent to a double bond, we also know that there can be resonance structures where the lone pair makes a bond there and makes a new lone pair on this carbon. And if you wanted to draw all of the resonance structures for this, you'd see that these can all resonate around. And if you wanted to draw all of the resonance structures for this, you would see that we can make a double bond here and here and here, and basically everywhere there's not currently one. So this whole molecule is in resonance. But as far as pi orbitals, just every carbon that has a double bond or has the capability of holding a double bond, like this one, they're all going to have pi orbitals. So to draw them all in, or I guess let's first identify the number of pi electrons. So it's just, there's 2 in all of these bonds plus these 2. So that's 2, 4, 6, 8, 10. So 10 pi electrons, and then the number of pi orbitals is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 pi orbitals and a total of 2, 4, 6, 8, 10 pi electrons. We'll do the same thing for question or part B. In this case, there's no lone pairs. There's just the 3, 4, 5 sets of double bonds. 5 sets of double bonds. So again, 2 electrons per double bond gives us 10 total electrons. So again, 10 pi electrons. And then every atom that has a double bond is going to have a pi orbital, because you need a pi orbital in order to have a double bond. So if I were to draw those all in, there's one here, 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 all the way around. There's not going to be any pi orbitals here because there's no double bonds on either of those carbons. So in this case, we have 10 pi orbitals and 10 pi electrons. So you'll notice that the number of orbitals is not necessarily always the number of electrons. You've got to make sure that you are doing both of those calculations separately. Moving on to part C. I think it's important to draw in the lone pairs if there are any. So I'm going to draw the lone pairs on that nitrogen. And then we have to think about whether or not those lone pairs are capable of resonating into the ring. And in this case, they're not, because the nitrogen already has this double bond here. So it already has one of its electron pairs in a pi orbital. So these ones are stuck in the hybrid sp2 orbital, so they're not going to participate in resonance. So the number of pi electrons in this case is just 2, 4. So 4 pi electrons. And the number of pi orbitals is going to be 1, 2, 3, 4. And don't get confused here. I drew this kind of around the lone pairs, but the lone pairs are not the ones that are in the pi orbital. The lone pairs are in a hybrid sp2 orbital, and then the double bond is the one that's actually in the pi orbital. And then for part D, I'm going to do the same thing, draw in my lone pairs, count up the number of double bonds, so 2, 4, 6, and then think about whether or not either of these lone pairs is capable of resonating. And in this case, the lone pair is adjacent to a double bond on both sides, so it can resonate into this ring. So we would say that there are now, so we would say that there's 2, 4, 6, 8 pi electrons, because only one set of the lone pairs is capable of resonating, because once you have one in resonance, the second lone pair would then be locked into the sp2 hybrid orbital, and it would not be able to participate in resonance. So 2, 4, 6, 8 pi electrons. And if we were to draw in the pi orbitals, we're just drawing one where all of the double bonds are present. And since one of the resonance structures on this molecule shows a double bond on the oxygen, there would also be a pi orbital on the oxygen. If you want to see what all of the resonance structures look like, I'll go ahead and copy and paste that in here so you can see what I mean by that. So here's what the resonance structures look like if you were to draw them all out. Go ahead and pause the video if you want to take a look at this, but basically you just, you'd have one of the lone pairs make a bond here, which would make a new lone pair on this carbon. So again, bond here, lone pair here, which can then further go around the entire ring. You can do that on repeat until you eventually end up with your original structure again. So that's why we've drawn this pi orbital here, because one of these lone pairs is capable of participating in resonance by entering into a pi orbital. And then lastly, for part E, again, I'm going to follow the same process of just drawing in my lone pairs. So this sulfur atom has 2 lone pairs and the nitrogen has 1. That way they each have a total of 8 electrons and their octet is full. So to figure out how many pi electrons we have, we need to determine if any of the lone pairs are capable of making a double bond. So the lone pair on the nitrogen is stuck in a hybrid sp2 orbital because we already have this double bond here. So this is not going to be, those are not pi electrons. However, we do have this lone pair that is directly adjacent to a double bond, which means that, and that's, again, same on both sides. So either way, it could resonate both directions, but only one of these lone pairs is going to be able to resonate. Once one is in resonance, the other one will be stuck. It'll be locked in the sp2 conformation. So that means that the total number of pi electrons is going to be 2, 4, 6. And to draw in the pi orbitals, we would have one here, and then one where all of the existing double bonds are. Oh, that was really bad. There we go. So that brings us to the end of this recitation packet. I hope this was helpful. I know this video was much longer than the videos I've made in the past, and that's because I tried editing it a little bit differently. Instead of just doing a voiceover, I was actively speaking as I was writing, which tends to slow things down. So this video ended up being a bit more drawn out, but I hope it was still helpful, and if you liked this style compared to the other ones, let me know and I'll probably end up doing more of this. It's a little bit easier on my end. It just means that my videos tend to be a little bit more imperfect, and you hear a lot more of my cuts and breaks and breathing and thinking and all of that tends to slow things down. So hopefully that wasn't too annoying. And if you have any questions, send me an email and I will hopefully be able to answer or clarify them.